Thank you very much. And first of all, I'd like to thank all of my co-organizers for making this happen, especially to Gabriel and Suresh, without whom this, if I were left to an organizing of anything, you guys will not be here. So my contribution to the organization of the event is purely spiritual. So welcome and thank you very much. So I was told by Suresh and Gabriel that I should give a two-part introduction to a fairly wide audience. As I understand, there are physicists, mathematicians, and a combination of people on how AI can assist with mathematical discovery in a broad sense. So let me just begin by sort of summarizing the progress of mathematical physics, where I got into this from the point of view of mathematical physics. So, I think it's indisputable that any combination of these nouns and adjectives is the right language for physics. Or not any, all combinations of these nouns and adjectives. And for example, if you talk about what gravity is, to a physicist, we say gravity. To an algebraic geometer, you explain to the person that it is a Ricci-2 form of tangent bundles. What is an elementary particle? Well, it's an irreducible representation of Lorentz group and certain sections of bundles with Lie structure, and so on and so forth. String theory, if you wish, is sort of a brainchild of this gauge gravity geometrization tradition of just trying to establish this dictionary between what pure mathematicians see and what physicists see. This is not a talk on string theory, it's just, but I will mention only very briefly on why a certain problem in string theory inspired me to get into the first place. So it's certainly, this is firmly established in the 20th century, but now we're in the 21st century. And really in the last 10 years, this has been a new exciting era, because between this dialogue between physics and mathematics, there's this one more person, this one more person. I guess it's not dialogue anymore, it's a trilogue of, and then that is inevitably computing. And that's been the last about 10 years or so. And by computing, I mean that there have been software developed to specifically compute interesting objects that arise between this dialogue. So slowly, words like SAGE, Macaulay 2, GAP, LMFDB, GRDB, slowly are seeping into both communities. If you don't know what these are, I will tell you a little bit about them. So this is almost becoming a sort of, once an acronym becomes part of your canon, it becomes part of the language. And it's very nice. And of course, as I say, this is very much of an interdisciplinary enterprise. So this is pretty much 20th century. This is the first decade or so of the 21st century. And what I like to emphasize that now in the second decade of the 21st century, there's an overarching personality, and that inevitably is the progress of AI and how AI would look at this conversation between these three different fields. And in fact, indeed, for those who don't work on it, what do I mean by AI? So let me just give, bear with me, I'm just going to give a two slide summary of what string theory is and why is it that this gave, at least what my background came from this area, and how this got me into this AI business. So quick summary, the one indisputable equation about string theory is that 10 is equal to 4 plus 3 times 2, okay? You can dispute it as much as you want, you can't argue with this. So what do I mean by this is that string theory is a promised candidate, still I think the best candidate for quantum gravity, a unified theory of everything in 10 dimensions. And we don't live in 10 dimensions of space-time, we live in 4 dimensions of space-time. And the classical solution, and this is back to the early days of Hall, Strominger, Witten, Vafa, and all these people, Strominger, Witten, Candelas, Horowitz. And the classical solution of the extra 6 dimensions is to take a 3 complex dimensional Taylor manifold with Ricci curvature 0. So otherwise a compact Fabian manifold. So if you don't care about algebraic geometry, it doesn't matter. the idea is to have extra dimensions because, we have a 10-dimensional theory of quantum gravity. We live in 4 dimensions, and to have these extra dimensions be modeled by some kind of 3 complex dimensional algebraic variety. So that's the bottom line. And the geometry of this algebraic variety will determine the physics of 4-dimensional world. So we're back to this dictionary again, this translation idea. So what is a particle? What is an interaction? Well, they are determined by the cohomology theory of this algebraic variety. What is a mass? It is determined by the metric on this manifold. What is a Yukawa coupling? It is certain triple intersection integral forms of the manifold. So now we have a specific computation that a physicist can take to a mathematician and vice versa, and then this dialogue. And I think many, many members in this, I think this half of the room have contributed widely to this dialogue. So I see a lot of my string friends here who've done some fundamental work. Gabriel's sitting in the wrong pile because I don't know this pile so much. So you should, but this is great. I mean, we don't want segregation. We want complete mix, and that's the purpose of this conference. So in some sense, string theory is a very good homage, if you wish, to Kepler's old mystical saying, where there is matter, there is geometry. So it's a complete geometrization of fundamental physics. So at the end of the day, so these are geometries in 3 complex dimensions, and you can take 3 possible views about why our universe is the way that it is. You could be anthropic about it. We are where we are because we see the world as it is. You could be, you could think that we are very special in the sense that you can select a certain 3 complex dimensional variety or generalizations thereof. But we haven't found such a selection rule yet. So this selection will be called the vacuum selection principle of string theory, which we do not have. Or you can take this multiverse idea that, we have this vast landscape and we just happen to be one possible in a parallel universe. In this sense, what string theory it has developed into is something that's actually very much in the spirit of NASA's exoplanet search. So the NASA exoplanet search, I think, is found about something on the order of 10 to the 3 to the 10 to the 4 habitable planets in a space of about 10 to the 7 observable planets, exoplanets. So 10 to the 3rd. And we will hope that out of this 10 to the 3, maybe 1 is like our Earth. So what string theory does is to search the space of these geometries and try to determine a universe that is like ours, or find a selection principle for it, or one of the goals. So that gives us the biggest theoretical challenge to this field. And this is where, so that's, I'm not gonna say the word string theory anymore. It's just that we're now translated to this particular problem, which is called the vacuum degeneracy problem. This is probably the biggest theoretical challenge of string theory, because we don't have a selection criterion, right? I mean, why choose one particular geometry? Or how do we know a certain geometry determines exactly our world with its particular interactions, its particular standard model, its particular shape of gravity? And there's no metric that we know of on this landscape of possibilities in the moduli space of possible solutions either that will select for something like this. So the ideas really go back to Douglas back in the turn of the century, is to study the statistics of string vacuum. And then KKLT in the same year gave this number, sort of let this number seep into the imagination in the public. Of course, this number is highly back of an envelope calculation. This 10 to the 500 is just a rough estimate of the typical number of algebraic cycles in a typical Fabio threefold. I'm going to talk a little bit about that. So it's a very sketchy. But somehow this number got into the public imagination because it's very big. Interestingly, if I take this number to a data scientist, he or she would just say, this is nothing. We deal with these numbers all the time. So awesome. And that's how this dialogue really started happening. And then this number in the last few years have actually been bumped up to as high as this, and probably more. So if you start looking at fluxes in F-theory compactifications, we're looking at numbers such as big as this. So, why are big numbers? Why are we talking about these kind of numbers, right? In the kind of scenario. Well, the bottom line is very, very simple. Algebraic geometry leads to combinatorics. combinatorics leads to exponential growth. That's it. That's very, very simple reason. So let me just give you an idea. So one of the constructions of, and I focus on Clavier because this is my bread and butter. So for Clavier, a Clavier one-fold is just a torus. It's flat. It's a one-dimensional, complex-dimensional manifold, and it's Ricci flat. So Clavier manifolds are just simply high-dimensional generalization of tori, in some sense. So here's one construction. This is a theorem of Borisov and Batirev, and the theorem is that if you take a toric variety constructed out of a reflexive integer polytope, then take that toric variety and take the anticanonical hypersurface in that toric variety, you'll get Clavier. So if you're not an algebraic geometer, that was just word salad. It doesn't matter. LLMs will probably treat that one day anyway. But the point is, an explicit construction of Clavier simply boils down to, this is certainly not all of them, but this is by far the largest known class of Clavier. All you do is something that you can explain to a high school student. You take an integer convex polytope. So in 2 dimensions, this is a polygon. You see, these are polygons. And these polygons have a very special property. Not only are their vertices lattice points, they have only a single interior point, such that all of the bounding faces, these here are just lines, is lattice distance 1 to the single interior point. So Borisov and Batirev's very, very beautiful theorem says that if you have this combinatorial object, you construct an auxiliary toric variety, and you take an auxiliary hypersurface, and that will be Clavier. So I won't get into the details of that. But the point is, now all of a sudden, our construction becomes completely a problem in combinatorics. Right. Now, here's an interesting problem. You can ask a high school student, how many lattice polygons can you draw such that there's a single interior point and such that all of these are lattice distance 1 to the interior point? Right. Up to SL2Z. So you want to quotient outbalanced, because if you deform by 2 by 2 unit determinant matrices, it turns out they're equivalent. This problem was solved by the Italian school of algebraic geometry in the 1890s. Fano, Del Pezzo, and these people. And it's a very beautiful problem. It's kind of cute that they were thinking about this problem. I don't think combinatorics developed enough for them to even phrase it quite in that language. But Del Pezzo and Fano certainly were thinking about these things. And they came up with a specification, essentially. And there are only 16 of these. And these are the 16. Up to SL2Z, there are only, so you can prove in every dimension up to SLNZ, there's always a finite list of these. In dimension 2, they're exactly the 16. So we take one example, my favorite one is this one. So this is a single interior point at 0, 0, and then this is -1, 0, 0, 1, and -1, -1. You can show that all of these are lattice distance 1 to the single interior point. I like this one because in algebraic geometry, this diagram corresponds to the projective plane, CP2. And if you take the anticanonical divisor of that in CP2, you get the cubic elliptic curve. And so, as we know, the elliptic curves are tori. So this is a very beautiful way of constructing. You get for free, in some sense, a donut. Yes. 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 And this is actually these are only toric ones. Yes, absolutely. Yes, that's a good point. Yes, absolutely. So they knew about blowups. They knew everything. Yeah, that's what they gave a complete. Absolutely. So, but this I'm only restricting to the toric cases. So this is interesting. So I mean, it's a problem. You can do. I mean, this you can probably do at home in high school, or if you're Russian, you can do this when you're in kindergarten, and then you can show there are 16 of these. And that's it. That was the entire progress up to the end of the 20th century, and that's quite amazing, right? Because what is the next number? I mean, obviously, right? What are lattice polyhedra that have this property up to SL3Z? Nobody knew, and the combinatorics worked on this for over 100 years and had zero progress. until physicists learned of this theorem, Boris of Batira, and physicists Kreutzer and Schalke learned of this theorem and said, well, hang on a minute, this is a great way to construct Clavier manifolds to start looking for string theory. So it's a convoluted story, but it's a very beautiful one because so many different branches of science converge to this problem. So physicists don't, physicists like explicit things, right? We're not completely satisfied just because Bhakti tells you something. We actually want this. So this guy thought, okay, well, surely we can do this on the computer. So in the 1999, sort of personal computers were getting pretty good. And so they thought, oh, we can just do this and run it and just by turn of the century techniques. So it happened that these guys bit the bullet, found a way to construct this polyhedron by method of pasting, and then ran on a Pentium machine for 6 months, if you even know what a Pentium machine is. And in 6 months, they found 4,139 three-dimensional analogs of these things. Where the hell does that number come from? No idea. There's no generating function for this sequence. So if you have a beautiful sequence, 1, 16, 4, 3, 19, that's pretty okay, whatever. But so for algebraic geometry, this number is interesting because they give 4,139 K3 surfaces as hypersurface in the toric varieties, because the one generation, so elliptic curve, this level of Clavier 1-fold, Clavier 2-fold K3 surfaces, so they're sort of unique in some sense. And then the one they really want is 3 times to remember, so Clavier 3-folds. So what is the next number? So 4,000, so it didn't look that horrible. But then the really impressive calculation, which took another year to do, which is year 2000, 500 million. So this is a very curious sequence, 116, 4,000, and 500 million. And now people have, people from GRDB, people like Corti and Kasperzik and that big collaboration have shown the completeness of this. If you check, verify, there is absolutely no more than this. And what the next one is an open problem. So here's a problem you can state to a high school student, and yet it's a complete open problem in combinatorics, which is relevant to mathematics in algebraic geometry, combinatorics, number theory, as you will see later, and extremely relevant to physics. Well, because combinatorics is very hard. So there have been various collaborations of physicists and mathematicians just trying to understand, this is already interesting. This is big enough. This data set is big enough that you can play with it. A little bit of technicality for those who care about algebraic geometry. This is actually just a very small estimate of the actual number of Clavier. So these are the actual polytopes. So for each polytope, there exists different triangulations, and each triangulation could potentially give a different Clavier. So it's estimated that the actual inequivalent Claviers in dimension 3, so these dimensions are the dimensions of the ambient polytopes you need to subtract by 1. So these polytopes is estimated is 10 to the 10 to the, I think 10 to the 10 to the 8, I think it's a recent estimate of the actual number. It is a conjecture of Yau that in every dimension, the topological type of Clavier varieties is a finite number. It could be 10 to the 10 to the whatever, but it's still finite. So, but this is still an open conjecture. It is a theorem that positive curvature of final varieties in every dimension is finite. So that's why we have this nice trichotomy in algebraic geometry. Final varieties are positive curvatures, like P1s and P2s. Claviers is the Ricci flat. And then everything above that is general type. So Ricci negative. And those we know are unclassifiable. I think it's some NP, it's equivalent to some Turing incomplete problem. Final varieties are finite in every dimension. That's a theorem. And Claviers just at the boundary. This is why Claviers are interesting to mathematicians and physicists. They just this beautiful boundary thing, and it's conjecture of Yau. In the best world scenario, Claviers, Ricci flat cases, have a finite number of possible topologies. You see this already happen in our familiar objects, right? So for example, in complex dimension 1, In complex dimension 1, we have Euler's classification theorem of the possible surfaces, which are oriented and compact. So that's the classical topology answer. The positive curvature things are sphere, that's it. The zero curvature thing is the torus. The negative curvature things are the two tori, the three tori, the standard things you see, like pretzels. And so indeed, positive curvature is the Fano variety P1, so because CP1 is S2. That thing is finite topological type, there's only one. In dimension 1, the torus, the boundary, there's only one, the torus. And then there's the general type, which is infinite. So you already see this even in the classical theorem of Euler. So in some sense, this is a big generalization to higher dimensions of this classical result we learned from topology. So when you're dealing with numbers like this, it's natural what you do, right? We're in the age of data, and you just try to see what data science says about it. But this is just data science. And people have been doing data science for these kind of things for the first decade. And something happened in the 2010s that the word AI kind of seeped into the public imagination, and then people started exploring. So I started exploring just because I'm completely naive to this. I started doing this in 2017 for a very precise reason. It's because Mathematica 12.0 came out in 2017, and Mathematica 12.0 has built-in neural network. So the first time I can actually play with something. And I wasn't the only one, so the people were kind of thinking, my friends were independently started thinking about how to explore the string landscape using not data scientific methods, but neural network methods. I was being a little more ambitious because ultimately what I wanted to do is to explore the landscape of algebraic geometry. So that's really what got me into, not just, forget about string theory, forget about all of that stuff. Can neural networks detect patterns in geometry? And then I became increasingly obsessive and increasingly like, can it start solve problems in differential geometry, number theory? And then I started making friends like Hyupon, who is a card-carrying number theorist, who taught me a lot of number theory, and I started exploring number theoretic and arithmetic geometric explorations in AI, which I'm going to talk about probably in the second talk. So this is nice. So 2017 marked sort of the beginning of an annual series which I was involved with. Is called String Data, and you can see, and the question is, how can machine learning techniques help with this vacuum degeneracy problem? Right, that's the initial motivation of this series. If you look at, by the way, 2017 was a good year because Sophia became human. Did you know about? Do you know this whole thing? This like Hanson Robotics developed by some company in Hong Kong, created this early sort of humanoid chatbot, and Saudi Arabia granted her a passport in 2017. So that really, this is the first AI non-human entity that has a human passport. And this is clear, this was 5 years ago, right? So it's clear where all of this is going. Somebody asked me a very good question. Can she drive? In a sense, because, in Saudi Arabia, it's a big controversy. It's a she. I don't know, you can Google what the answer to that is, but it's a very deep ethical question. So, the question is, yeah, sorry, comments most welcome. If you look at my last bit, how do I get rid of it? Smooth. There's a crop. But I think it's on a different laptop. Oh, yeah, there we go. High tech. It's like, I have no idea what that laptop is doing. It's not even mine. Pretty cool. So for the string theorists, my last slide for string theorists. If you look at the progress where string theory is going, you see here it's a sequence of all annual conferences. So the relevant ones here is the cute one. The string math started as late as this decade. You would have thought that string math would have been much earlier, but somehow it didn't. The first strings annual conference was in '86. String Pheno started in 2002. String data started in 2017. And so actually with Mishra, I think it's probably online. We organized one here just last year in Cambridge, and the next year will be Caltech. Was it not? So I think, yes. Yeah, but it was not called string math. I think it's kind of, why didn't they? I see, exactly. What did you call it? Okay. So that's it. So at least the brand started in 2000. It's a good point. I should make a note of that. Anyhow, but now apparently there's an M theory in math, which started in 2020 in Abu Dhabi. There's a new series by Hisham. Okay, that's it. So back to this. So the basic problem that I was thinking about was a very, very naive, just because I didn't know anything about machine learning or neural networks. So I like giving these talks because I can share my ignorance with the audience, and then you can tell me what I should actually be doing. So a typical calculation in algebraic geometry. So this is actually a powerful, this is a very ambitious statement. The field of mathematics known as algebraic geometry is an image processing problem. I've said this several times in front of mathematicians. I'm still alive. I've not been shot. So it's still okay. So, it's like, I don't know how Grothendieck will feel about this, but hey, why not? So in the following sense, right? So a typical calculation in algebraic geometry is the extraction of certain integer invariants from a certain tensor configuration. And that is true for any algebra. So algebraic geometry is the study of set of the vanishing loci of set of polynomials. But this is a very down-to-earth definition, but that's what it is. And then computational algebraic geometrists do, people like what Macaulay, people like Hao Shank and Stillman and Grayson, they take this idea of algebraic geometry and then program that into Grosvenor basis reduction problems in Macaulay 2, and that's why Macaulay 2 is so powerful. And so despite what Bourbaki tells you, don't believe in Bourbaki, because Bourbaki is incomprehensible in the most beautiful and austere way, but it's not human. Bourbaki is not for humans, it's for gods. And for us mortals, algebraic geometry is about configurations of tensor inputs, right? And then you compute, I don't care what it is. For example, a typical computation, you want to compute the Hodge number H2, 1 of this, an algebraic variety space. So to tell you a little bit of what this configuration means, for example, here is a complete intersection of 8 polynomials in P1 cross P1 cross P1. Now you can embed it into products of projective space, known as a complete intersection Clavium manifold, but it doesn't matter. This records its degree, right? And you want to compute some topological invariant. It's important that it's sufficient here to record the degree because it's a topological invariant, so you wouldn't depend on deformations, complex structure deformations. So that's it. So what does Bourbaki tell us that we should do when confronted with this problem? Well, you chase sequences until you're blue in the face. And it's standard what you need to do. People like Leray and these people develop cohomology theory in order to address this problem. So you do Hodge decomposition, and then you chase the embedding sequences into the good thing about algebraic geometry is because there's always an embedding space. So unlike differential geometry, you get sort of a tangent restriction, tangent shift restriction for free because of an ambient space. So you get this, and then you induce some short exact sequence into long exact sequence cohomology, and then you get some answer. There's a classic book of Tristan Hooch, which explains this, how to do this algorithm for physicists, which is a wonderful book. But luckily, this has been, this entire, of course, this is just a very baby version of it, but this has all been implemented in Macaulay 2 and Sage Math. Oh, great. So I could just, in principle, type in the quintic and get H11, it's H21 got 101. Yes, absolutely. But anything above the quintic, you're completely sunk. The reason for that is that the bottleneck in algebraic geometry is the determination of the Grosvenor basis. So the Grosvenor basis, algebraic geometry is, I think the more computational people I talk to, algebraic geometry is nonlinear algebra, right? Because linear algebra is sets of linear equations. You record its coefficients and you do Gauss elimination. Gauss elimination is polynomial time, or n log n maybe, but certainly not exponential. The analog problem in algebraic geometry is not to reduce the sequence of linear equations, but a sequence of, or a set of polynomial equations, multivariable polynomial equations. And the analog of Gauss elimination is Grobner basis. In fact, Grobner basis for degree 1 reduces exactly to the Gauss elimination problem. But unfortunately, once you have, even starting from degree 2, that this algorithm, Grobner basis algorithm, is a double exponential complexity problem. So you're completely sunk. So Sage Math will do the simplest cohomology or any Koch number, Betti number computation for you. But the moment it gets a little bit hairy, like 500 million toric varieties, age of the universe. Many, many orders of magnitude age of the universe, if you do it on that.
Calculate just the Hasselbalch zeta function gives you the Hodge numbers.
Yes, well, yeah, of course, you can do other tricks of that.
But isn't that, I don't know. I mean, I don't know whether it's much better, but do you know?
In general, it is still very, very difficult.
But people really try.
I think so. Yeah, I think there are even packages in Macaulay which uses exactly the Zell function method, but it's still too difficult. I think Q1 would know about the complexity of maybe like, L function computations. How complex is that? I don't think it's like linear time or polynomial time. It gets
Go over all the primes.
If you go over primes, then it gets complicated anyway.
So bad.
But that's a good point. They're shortcuts, but for brute force, not so much. So fine. Nevertheless, there exist databases in which people have computed these things, inspired by Hubsch and friends, and Candelas and friends, and Albrecht as well. I think you did some of the early calculations in these Hodge numbers. So these guys have been giving us data for 20 years. And the database grows a little bit of the known cases. And then it becomes an image association problem. Right? At least that's what I was thinking in back then. Because Mathematica 12.0 came out. And also because I was on parental leave, my son was born, so I had time to just like think about random stuff at 4 a.m. in the morning when you can't sleep anymore. So picture this, take this, interpret this as an image, and this is an association rule of this image to the number 22. Now, this seems like a pretty nonsense idea, right? But just try it. If you can give good accuracy, then it shows there's something about pattern recognition in algebraic geometry in a way that algebraic geometries are not doing it. And it is a good estimate of what it should be. So in light of that, I think Gabriel asked me to tell a little bit about a machine learning approach to algebraic geometry. So this problem is a standard problem. It's the problem that every machine learner starts by learning, which is this image association problem. So this goes back to the digit recognition problem. So there's a database by NIST, the National Institute of Standards, which started in the 1960s. Can you believe that? They got hundreds of thousands of postgraduate students over half of a century labeling things like this by hand. So that it's an incredible human endeavor. So now they have the database of handwritten digits to pictures of whatever, and they got people just sit there. They get paid by the hour. This is a 1. This is a 2. This is a picture of a mouse. This is a cat, and they've been doing this since the 1960s. So it's freely available in NIST. So the classic one is the hand digit recognition. So this is a typical sample taken here, and if you want to do this problem, mathematically, it's actually quite difficult, right? How do you know this is an 8 and this is an 8 and this is a 2, right? You can as mathematical physicist or as a pure mathematician, maybe I can try to find a very clever Morse function to try to set up the topology of these sequences of these things. You can try it, you won't get very far because there's so much variation, and then the computation complexity for topological, combinatoric topology is again exponential running, and you're sunk again. So So what one does in machine learning is to take databases like this, feed it through a neural network, and then try to estimate with certain probability what the output should be. Right. So my idea was just similar to take images of algebraic varieties and take the known labeled cases. So we didn't have databases from 1960s because we didn't have 100,000 graduate students labeling for 50 years. But we have pioneers in the field giving us this Hodge data, so we can actually label and try to machine learn that. So now Gabriel tells me to give a mini. I'm assuming that this audience, not everyone here is familiar with machine learning, and would not mind a mini tutorial. Okay. So, well, I mean, I'm going to give it in a very, very babyish way because I learned this only recently. I'm certainly not a CS person. So here is a tutorial on machine learning in, I don't know, in maybe for the rest of this talk, and then the next talk I'm going to say how to apply this method to geometry first, combinatorics next, and then number theory finally, where we got very excited with this recent work I've been doing with Coupon. Got very excited, sleepless nights, because there was an AI-assisted human discovery that was unexpected by the number theorists. So, machine learning 101. Okay. So back in kindergarten, we all learned about regression. So in the following sense. If you're given a set of data points, right, and now everything is of course jazzed up. Now we don't, we call this point cloud just because it sounds sexy, but all it is just, a set of vectors in Rn. But data scientists like to reinvent words to make it sound cool, but once you get under the hood, you get to say, okay, this is not. But cool names are cool. I mean, they're important because you get stuck. This psychological game by naming something is extremely important. It's half of the game. So back in kindergarten, if you're given a point cloud, not only there are no other. So that's what you do. That's what you do it is that you can clearly state minus as independent variables and one of them as a dependent variable and do a best fit function. So that's what's called so that's just regression. So now we have a slightly more sophisticated name for this in some sense. Type 1 is now roughly called unsupervised machine learning. Type 2 is roughly called supervised machine learning. Supervision comes because you're isolating one particular variable and you're trying to see its dependence, and you're supervising some neural network to try to pattern match towards that output. So the classic Bible, which I recommend everybody to read, is this Goodfellow, Benjo, and Corville Deep Learning 2006 MIT Press. This is this is the Green-Witten-Schwartz of deep learning. It's the Hartshorne of deep learning. And so it's interesting. I've taken this picture directly from and then this plot directly from this book. So it's interesting. In the 1940s to 1960s, the word cybernetics was big, and so they plotted the word cybernetics. In the 80s to 90s, the word connectivism was big, and I think that was this one. And then neural networks. I didn't include the rest of this plot, which is neural networks started exponentially increasing in literature. So this is a collection of all text on Google Books. So somehow neural networks and deep learning is the brainchild of connectivism, which is a branch out of cybernetics. It's a very old field. You know, it really in the 1960s, just around the time when the Birch-Swinton-Dyer conjecture was coming about. And there's a deep reason, a cultural reason for that, which I'm going to get into. You know, why was Birch-Swinton-Dyer thinking about this when they had these early things? And the point I want to emphasize, which is I'm just quoting good fellow Benjamin Corville, is that somehow from the mid 2000s, this very old idea of using a so-called perceptron, and I'll define what that is in a minute, became part of our day-to-day experience for a very simple reason. Is because this thing here has GPUs. Very tough. One of the basic reasons. It's just because we now have at our disposal, each of us, a supercomputer. What would have been considered 60s a supercomputer, which is not possible at the time. I mean, they were thinking, I mean, these people were smart in the 1960s. They were really thinking about, you know, the first AI experiment. I really should use the word AI. I mean, because they are doing links of neurons. They had a wall of cadmium sulfate photoreceptors, and they had flashlights trying to trigger each of them and try to do a neural computation that way in the basement, I think, that at Penn. That's quite incredible, right? But the point is that we're doing exactly the same thing today. But the thing is, we don't need a wall anymore because we've got GPUs in our laptops. So we can just run, you know, Mathematica can, even Mathematica, you know, we're familiar with this. And of course, then if you want to go serious about it, you have to use Python's PyTorch or TensorFlow. And that we're talking about a matter of seconds for hundreds of thousands of neurons addressing databases of algebraic varieties in the hundreds of thousands. You're talking about seconds. I'm sorry. Oh yeah. Sorry. Yeah. So yeah. I'm mentioning BSD because in the 60s, BSD was doing one of the first computer experiments. And I will get back to that, a lot of my second half of my talk will be devoted to BSD. Okay. Yeah.
Has the conceptual foundations changed since 2006? I mean, why is that?
My naive understanding is that it hasn't. But it is very much an ongoing work to understand the interpretability. One of the biggest things is to figure out what is happening from the point of view of statistical physics, what these neurons are actually doing. And that's an ongoing work. But to my knowledge, I don't think there's been a major conceptual breakthrough. Is that right, Robert? I mean, you thought much more about this. But so they need us as much as we need them. Robert had a nice paper of interpreting neural network as RG flow, and David Berman is because they want a theoretical model that's groundbreaking, but I don't think we have that yet. It would be great. So, but hey, conceptual breakthroughs aside, it's great. You can experiment, and that's like totally cool. Right, on a laptop in a matter of seconds, you can just cheat. So the most key mathematical tool, just very briefly, is gradient descent, because it's an optimization problem. Basically, a machine, neural network or anything is trying to find an optimization problem, and this is why, even if you're trying to compute odd numbers, can you find in the space of possible guesses something that will converge towards an answer that's correct? So that's basically that is the same as this. Number 3 experiments I'll mention later. Can you find certain patterns in distributions of L functions that will converge towards a certain pattern? So gradient descent is just basically, like, I guess, who did this? I think it's Laplace. I think it should be attributed to Laplace or Cauchy. Maybe Cauchy, they knew about this, right? So how do you find a local minimum? This is the repeated one central conceptual idea of all of machine learning, is this very, very fundamental thing we learned from Cauchy and Laplace, is how do you find the local minimum of a function of multivariable, a differentiable function of multivariable. So you usually just do iteration. You take an epsilon, take some coefficient of the gradient of the function. It's called gradient descent, and you do steeper descent as you go iterations to try to converge towards this minimum. So the reason I mention this is because this epsilon has it's called learning rate. So if you hear about the word learning rate, so that's what this epsilon means. So again, epsilon for us is a coefficient, right? But once you call it learning rate, it certainly sounds like, oh my God, it's so cool. But that's all it is. And the initial value for where this descent starts is a type of parameter that's called hyperparameter. Again, for us, it's initial value, or whatever, right? But once you call it hyperparameter, ooh, it sounds sophisticated. So one thing, just as a comment, sometimes you're not sure which path to choose to converge to your optimum. So you do some kind of statistical variation. So that becomes like what's called a stochastic gradient descent. Stochastic gradient descent. So typically, f is what's known as a cost function. You're trying to optimize a function which has cost, and once your cost is being minimized, then you know your neural network or the likes of a neural network is converging towards the right answer. And I'm just giving you demystifying buzzwords for you. This is basically what this little talk is about. When you, of course, then you take data, right? Your data size could be very, very big. So you usually splice your data into chunks, and you feed these chunks into this your cost function to have an estimate how it's going. And these chunks are usually called batches or mini batches. So that's it. And the basic types of algorithms or machine learning algorithms can be sort of divided into two types: discrete type of problems or continuous type of problems. The discrete ones are typically called classifiers because you're trying to classify something, and the continuous ones are usually called regressors, because that's sort of a nod towards regression, because in case you have a continuous function and you're just trying to do a best fit, as it were. So the neural network version of a regression is called a regressor. Cool word. And then, so that's one division. The other division is supervised versus unsupervised. As I mentioned earlier, these two things that we were taught to do in kindergarten, which is to look at the data. Unsupervised is you just simply try to observe the data structure as it is. So what can you do with this? So typical things you want to do are like cluster analysis. Does your point cloud fall into natural clusters? Autoencoders. Can I transform your data into a certain way into another representation and to see whether that does better? So so autoencoders they're two-step process. They are the encoders and the decoders. I'm telling you with these buzzwords. Well, at least most of my effort was just trying to demystify for myself what the hell these words mean. But now, finally, at least this is how I understand them. Like, it's probably not very precise, but I finally understand. So autoencoders for us is just the transformation on the data to see whether if I don't immediately see a structure in the data, can I represent it in another way by, for example, a linear transform? That will do it. I won't go into GANs, but there's a very nice one that is of this encoding mode. This is not an autoencoder, but it's a nice way of encoding, and it's called principal component analysis. And this is a way of reducing the dimension. I'm going to go into that in a minute, because this method was very useful towards the experiments that Kyu-Hwan and Tom Oliver and I doing on the BSD conjecture related all this stuff. And I'll get into that bit. This is very nice one. I'll go into that in a minute. So these are the unsupervised. You have given this data cloud and trying to do what you can do. Supervised one are labeled data. So by labeling, you see, for example, it's like one example is to pick out one dimension and call that the dependent variable and label the rest of them as it is. So the ways to address it are, so one thing is called the perceptron. This word has fallen out of fashion. Anything that ends in tron, it was probably invented in the 60s. The word perceptron is, I will define in a minute, it's just a feed, what we now call a feed-forward neural network of multi-layers. Other cool things like support vector machines, which I will mention very briefly. And there are other things like, various other classifiers, supervised classifiers like decision trees and Bayesian. And there are various, of course, this is a very baby summary of the various techniques that you use. But basically you have two types, discrete versus continuous, and supervised versus unsupervised. So a single neuron, which back in the day was called the perceptron, is just a nonlinear regression problem. That's it. There's that end of story. There's nothing. Definition: a neuron is a nonlinear regression problem. Okay, in the following sense. Of course, it sounds so much cooler if you call it a neuron, right? Well, all it is that it imitates a neuron by having an activation function. Right. So what I mean by this is, so for example, you define an activation function, or you take it to be analytic. It doesn't have to be. For some input tensor, you could have multiple. The idea is that your input could be very complicated, right? High dimensional input. And for some multi-index. And you consider some activation function. I will give examples of activation function in a minute. So a single neuron is just this activation function. So if you don't think about it in terms of neural networks, this activation function is what we call regression by the function f back in the day. For regression very much relied upon the fact that f is a simple function and differentiable. But the key point is that a neuron does not have to have even an analytic function, and you have multiple links of such neurons, and that's what gives, in the 80s, called connectivism induces complexity. I think that was the jargon in the 80s and 90s. So, and then of course you don't typically just have your input. You may want to linearize it a little bit, right? So you apply a general affine transformation. So the affine transformation will have some, of course, I here is multi-indexed. So it's not just the vector multiplication. Your Z could be a very, very high dimensional multi-index object. And so these W's could be tensors that contract into them. So but it's an affine transformation. So this affine here, this is the linear bit, and that's the affine shift. So these W's are called weights, and these B's are called offsets or biases. So that's your function. And then you do exactly what you do in regression, which is to, one, have training data. You split your data. So if you're given a data set, you split your data into training set and validation set. Your training set is the one that you feed into this f to minimize f or some other associated cost function in order to determine w and b. Okay, it's you take all of this, you find the optimal set of weights and set of biases to make this function the best fit as possible. So exactly like regression. Okay. So that's the training data. And the validation data is the data that you've not seen, that you're not using for your training. And then because now your function is rigid, after training, your function is it is what it is. All of your W's and B's have been optimized to minimize, say, distance to this function, like in regression. And then you take this, you apply it to the validation data, and you find some measure of how bad your fit actually is. That's exactly typically. So the only thing that this is slightly different from regression is that in regression, sometimes you just do it to the full data set. But here, what you do is to split it to your training set and validation set just to check how well you're doing. So you apply to a chunk of it, possibly in mini batches, to make all of these W's and B's rigid, and then you evaluate it on the complementary set, because the neurons have not seen this before, and you want to see how well your fit actually is doing. So, and this is a typical example of a supervised machine learning. You're teaching it to make this xi. Regression is a typical example. These functions, the favorite examples are, just the sigmoid function. The favorite examples of these functions typically go like this, or the hyperbolic tangent functions go like this. Why? Because you imitate neurons. If you look at neuron firing patterns, they do nothing, and then you shine light on, boom, right? And you can even do things, funky ones. Here's a cool one. The ReLU function is just nothing, and then the x. So this is a non-differentiable function. But so then a metric ReLU is that you fudge it a little bit, another parameter. It's a typical activity. The linear identity function is also good, because remember, this is trivial function, but in a neural network, this is not trivial, because remember, all of these, you need to apply affine transformation. So before you use it in the neuron. So the linear, or the identity function, is actually the general affine transformation function. Right? So you should think of all of this, all these ReLUs and sigmoids and hyperbolic, it's with this affine transformation. And other things like softmax, and they have names. Once you have names, they all sound cool.
And what happens if you choose something like with a maximum? I mean, if you just
just like a max of, well, sure, you can do that.
But I presume they don't work. I mean,
no, I just have no. I think people do. They're like, this one max out.
Or something like sin x. What if you just,
oh yeah,
there's a very specific set of functions you've got.
Yeah, I don't think you need to go as sophisticated sine, because in some sense, sine, the Taylor series in sine, you're approximating that by this anyway at some level. I tried sine. I think I didn't do any better or worse. Yeah, and in fact,
to some fail though. I mean,
yeah, I don't know, but I think if you do study exactly, which classes, I'm going to give some universal approximation theorems which say that ReLU is good enough. There's a theorem that says a neural network composed entirely of ReLU, just this function, just if you have sufficient number of neurons, you don't approximate anything. So no need for. But of course, for certain specific problems, you may want to choose something tuned to your problem to reduce the overall size of the network. So this was a recent one. That's a really nice one, was by Mike Douglas and friends, where they used polynomial activation function to compute metrics, because these metrics problems are going to be polynomial in the variables you come in. So they say, oh yeah, we should use a polynomial activation function, and the neural network community got excited about it because they never thought about using why, right? But that one was very good in finding metrics. So just basically try your grandmother's kitchen sink until it works. This is about how far we're in the theory. Maybe this is but maybe not. Yeah, sorry.
Step function that you can really classify, like separate data sets. So any function doesn't have this property,
Yeah, so you're right. So the
sigmoid kind of thing.
Yeah, the prototypical ones were sigmoid and hyperbolic tangents. So those they work very well in classifiers.
Okay.
And they still do. But you can certainly try, and I would mention this ReLU thing. This is not a step one, and yet sufficient number of this will approximate.
Will make the same.
Yeah.
Okay. Thank you.
And yeah, so I know you can try. Yes, please. Yes.
So you mentioned this connectivity equals complexity. But isn't there also some influence of the nonlinearity of the activation function in that complexity increase? So I guess if you take the linear, this is kind of the known story from the early 40s or so, no?
Yeah. That's a good point. I don't know, a theorem where it says if you just use the identity function, you can find a complex enough network that will approximate anything. You probably not. But just ReLU is enough because there is that nonlinearity. But I wouldn't be surprised if you just use the linear function, you can approximate a lot of things. Or certainly any analytic function you can do because of Taylor series. I think that's probably true. If you just use a big network where every single net function is linear, possibly you can approximate analytic functions. I'm not sure.
Yeah, perhaps a comment. Yesterday in Johanna's talk, we had a very interesting example. She was showing the MNIST data set, but instead of like guessing the number at the end, the idea from what I understood was that neural network wanted to get the exact pixel picture that you started with, right? Yeah, exactly. So okay.
Sorry, I missed your talk. I would have loved to listen.
So
my train came in too late.
So we started with giving numbers, numbers, and then at the end of the, putting it through the network, we have to keep over, the network. We got some result, and then we just compare it with the little one, and then using the second method, the training of we then adjusted the W's and the D's to make the result the most similar to the beginning, and then we started over. And so I think we just put a default. Start over. And,
okay.
And every time you get your W's and D's to be more precise and such that the output goes more.
Well, probably that was not the correct, like the most general example, but I from what I got, you were suggesting that an infinite network would not do the perfect job. A network made up of infinite layers. And then,
yeah, I have to.
Yes, sorry, we go stand on the.
Okay, I was looking at a very specific case. Okay, so which was one feed-forward neural network, and where we took these W's and B's to be Gaussian distributed. Okay, and then we were able to have a phase diagram made out of the variances of this W on the slide. And so the idea was to calculate a particular correlation. So for a given layer, we had the correlation between these activated functions. And so if you have a correlation, you have a correlation length. So, and then of course, if your network is deeper than the correlation length, then you cannot learn anything anymore because then there's no correlation in the data. So what I was showing there is this example that you had this phase transition between an ordered and a chaotic phase. And in the chaotic phase, you don't learn because things are chaotic, but in the ordered phase, the differences get washed out and you don't learn anything. So you want to sit at this critical line. So, and then I was saying, of course, in principle, you want as big as network as the bigger the network, I think you probably agree, the more you can actually fine tune things. And while, as explained yesterday, of course, then processes get more complicated. But so if the network is bigger, then you have as this correlation, then it's not going to work. So that was the idea. Okay, sorry for the long.
No, it's fine. That's great. Thank you. Yeah, so fun things to try. And then, so coming back to this point of, so after you've gotten these activation functions for your typical regressor, your perceptron, I'm just going to use outdated words, old-fashioned guy. Then you need to establish common loss functions. So the loss functions typically are things for continuous loss function. For continuous problems, you typically use square error loss. So this is one that you remember from like regression 101, start 101 in your first year, right? Use the square of the function to its prediction. For discrete problem, you usually what they call categorical classification problems, that you typically use cross entropy, which is this is something based on Shannon's logarithm. And then you can just use it, and then you have this function. You try to optimize this function by feeding in batches of your data to minimize this in order to make rigid your weights and biases, and that's all you're trying to do. I'm still talking about just one function, right? The magic comes in precisely when did I get this point? When you put a lot of them together, right? So this is an architecture. So how you link these neurons together is called the architecture. This is an architecture of a typical feed-forward neural network. What back in the day was called the multi-layer perceptron. It's no longer a perceptron or a neuron, but a multi-layered version of it. Of course, it doesn't even have to be, it's feed-forward because all of the arrows go this way. So your input, this is your input layer, which could be, which is split into different inputs of these neurons. And all kinds of crazy stuff happens in between, right? And then you feed them out to a output layer. Everything between is called the hidden layer. This is called the width. This is called the depth. So the deeper, the larger the number of layers, it's called learning, and the larger number of width, it's called limit. That's it. And that's the magic. The magic thing is that this, even a structure like this, is enough to approximate anything. Of course, you can even do fancier things like putting arrows backward. You could have backward structures as well, just perfectly fine. I think that some of them is called GNNs, graphical networks, where you just give any directed graph and put neurons on it and then try to do stuff with it. Once you have this stuff out, let me just try to say, you use your typical measures of how well your predictions are doing with the typical measures, like coefficient of determination. I'm not going to bore you with the details of this stuff, stats 101 that we all forgot about. You can just look it up in the book. You want this, so once you validate on your validation set, you want measures like this to be closest to 1 as possible, to just see how good your thing is. So there's naive precision, which is how much. So in a discrete problem, there's naive precision because you predicted a certain set of, say, integers that discrete, and then you have an actual set of integers. You just find the difference of the two, and that's naive precision, or percentage of them actually agree. And you want that to be as close to 100% as possible. There's an extra check, which is, so of course you can also, for classification problems, you can also have things like confusion matrices, which is you predict so many categories. These are the actual categories, and how many of them you misclassify. And you want this to be the identity matrix as well, the diagonal matrix in the ideal case. One more thing I'm going to use, I really like using this MCC. There's some papers that I don't understand that say that MCC is extremely good as a measure for against bias, against false positives and stuff like this. So what the MCC, the Matthews correlation coefficient is the square root of chi-square in a discrete kind of problem. I'm going to use this. The reason I'm introducing this very briefly is that I'm going to use this kind of lingo in experiments that I'll be showing in the next lecture. Again, you want this to be as close to 1 as possible. If it's 0, it's randomly correlated. If it's -1, it's anti-correlated. So this is a very nice measure. Then it's here are these wonderful theorems, which I'm not going to. These are better off not read. Here's typical examples of where words fail. Theorem says this way you can approximate anything. Second theorem says this way you can approximate anything. And the third one is very interesting, is Hannin's-Relou's theorem, is that just using the Relu function, you can approximate anything given sufficiently complex neural network. I mean, that's a quite, I mean, of course, it's a massage and analysis. It's a deep massage in analysis, but you kind of intuitively, well, this one's that, just this shape, if you have sufficient of them linked together, you can approximate any function up to some definable measure. What is my oh gosh. Yeah. Yeah. It's the output of your neural network composed of all of these values. Is some input function that you want to model. So this basically says that this ReLU network will approximate any F.
So maybe I missed the definition, but I thought the ReLU was defined as R of X equals X if X is greater than or equal to 0.
Sorry. Yeah, sorry. This capital F is but it's complicated, right? It's going to look like this, where circle it's just this. So you link this theorem guarantees that this will do, and you can it's amazing. You can actually you can do it. You just type up. It's few lines of code in even in Mathematica, and in PyTorch it's just about this. Function. It's kind of amazing. Trying to find favorite function. I think I'm the sickest. Like Lercher's, geometric, and just few ReLUs, few layers would instantly look exactly at the plot of that function.
ReLU is better than the sigmoid?
I'm not sure better, but at least this theorem says the ReLU is good enough to approximate anything.
But
I think
a theorem for the
for
sigmoid.
sure it'll work. I bet my money on it. If you
Okay.
give me, I don't know, Weierstrass P function, and then just the 5 layers of 10 neurons each, will approximate it to arbitrary position very quickly. I'm just so overconfident. Give me any function. If here's a network that whose code is 3 lines, I will, in few rounds of training, I will approximate that function because of theorems like this.
Where the 5 came from?
Sorry, one variable. I mean, your theorem. No, sorry. No, this X is n variables. Oh, yeah, it's multivariable. So now you're right. So now you're.
So I'm sorry, I've just somehow missed the point. I mean, a function. This function. That's one variable.
Of one variable. Yeah, I think that should work, right? That's for n equal to 1. But I could. Have you tried something like that? So give me your crazy function, and okay, no, I'm being over. Yeah, okay. So if you obviously if you try to the prime counting function, I'm not going to be able to do this. There's too much variation. No.
Understand what you're.
Trying to think. If you just gave me one variable, you should do as well. I think you can find, yeah. So if you basically, if you just the function you're going to give me would just be a pair of points now that I'm going to plot out, and I'm just going to find a neural network using only ReLU or a hyperbolic tangent to approximate these pairs of points, say a continuous function. I think it will be you'll very quickly find it. Yeah. I couldn't get that one out. I tried, believe me. I even tried something like that, but I couldn't get her. Because I mean, of course, the prime counting functions you can get, because that's just x over log x.
Yes.
So you can approximate, you will find a shape like this. But if you want to find the finer features of all the oscillations,
That's the theta function.
I don't think you will get it.
I can show you. Well, I haven't done with ReLU, but I have a thing where you just use Riemann's explicit formula and you can.
Oh yeah, of course.
Yeah.
Sure, yeah, sure. Of course, yeah. The explicit formula will get the oscillations, but that's a pretty complicated formula, and you need to sum over all the critical zeros.
Yeah. You need a list of those things, but.
But if you want to just use a ReLU neural network to try to get the finer features of all. Like,
So the question was to quantify how well the training works. Okay, so how well the network learns and how fast and with a minimal architecture. Now, if you look at your theorems, you kind of, the theorem kind of proves that if you just wait long enough, any network is going to learn anything. I mean, to put it, is that what you're saying?
yeah, I guess so. Yes.
Okay, so
Okay.
so I just trying to put this into perspective to what I was discussing yesterday, where it was using some inputs from physics or information geometry to get some observables that really quantify how well your network works and how you choose your initial parameters to get a quick output with a minimal configuration. And okay, so I guess this is a slightly different question from what these theorems are.
I think that one of the key things of all these theorems that you need infinite. Yeah, it really works in the whatever the large is, and people have done work on estimating what this large is. I think in that sense, and it doesn't say anything about training time. Yeah.
Okay.
So given infinite training time and infinite size, I think you'll be able to do it.
Okay, thanks.
But of course, that's not practical. I think a lot of the work in the neural network community is to quantify that exactly. That's a very big area of research.
Exactly.
Yeah.
Thanks.
I mean, that's makes it.
Prime counting is so good. Yeah. I'm not sure. Yeah, that's for another conference. My friend Challenger will give a set of lectures on this, and he's now thinking very much on this actual architecture. I think whenever he's giving his talks. When he's coming? Next month, okay. So you can yeah, I guess the Lebesgue, I mean, I didn't go through the proof of this. The Lebesgue is probably most certainly needed for the ReLU, because that's the restriction. You need just the ReLU approximation. But the outcomes. I'm impressed people are actually reading this work. I'm not going to read it. It looks good to me. So how am I doing on time? I think I'm out of time. It's an hour and a half each. Oh, I did. Okay, right. Cool. Great. Right. And I thought I was giving a 1 hour lecture in total, and now it's become 3. This is a typical phenomenon as I've machine learned with my experiences with Gabriel and Suresh, that it's almost twice, it's always at least twice longer than I think. Like when I visited you guys in Lisbon, I thought I was giving like 3 hours of lectures, and it quickly turned into 9. Yeah, but I was paid well in bottles of fine wine that you have fed me. So one thing I want to emphasize, two very cool things I want to mention, just to finish off, are 2 of my favorite things that are not neural networks. So this is sort of the neural network side of things. are support vector machines and principal component analysis. These are very interpretable. But the reasons I'm like obsessed with them. I mean, they're similar things, but they don't have, because when we're talking about 100,000 neurons, and typically that is about how many you get. How do you even know what each neuron is doing anymore? And how do you for us, my various collaborators, I mean, our deepest goal is, how do we raise a conjecture in mathematics? Can it give us a new conjecture in mathematics by looking at this? And neural networks are not that useful, because how do you know which of the 10,000 neurons is doing what to make a concrete statement? But so I'm going to mention just to finish off today, support vector machines and principal components. These are a little more interpretable, as Kyuban and Tom and I found. And that can actually start this. That's what I mean by the AI. Why this talk is called the AI Mathematician. I'm not interested in any of this machine learning stuff. I'm interested in, how do I use this to help me raise a conjecture that I can take to a number theorist or algebraic geometer, and he or she can actually prove this. And that's what, I mean, this is the idea of what the field is actually going. So support vector machines. So this is again a problem of supervised learning. And it's a very nice problem. And it's just to find hyperplanes that separate label categories. Surprisingly, I'm going to use this to simple finite groups later. And I was very surprised that support vector machines was able to spot a new pattern in the distribution of simple finite groups. And that's for next lecture. So what do you do? So, you have like a bunch of black dots and a bunch of white dots like this. They're labeled because I've labeled one black and one of them white. Of course, it could be much more complicated. The idea is, how do I find the optimal separating plane between these? So the support vector machine is just a cool way of saying, finding this red line or red hyperplane. So, so you write it, so is that what I wanted to say? I think that's what I wanted to say. Why do I say two hyperplanes? So, okay, so I have a bunch of data labeled by 1 and -1, and I want to find a plane such that one of them is bigger than 1 will give all of this data, and one of them is less than -1 will give the -1 data. And the distance between, that's these two, these two. And I want to minimize the distance. Obviously, I haven't read this slide for quite a number of years. And I want to find you can help me if you wish. Why did I just write this? You need the two planes. I want to find the two planes closer, like the one in blue, right? And the one in green, right? These are the two planes, and such that I want to, but how do I get I mean, obviously what I want is the red one. Closest to one. You have like a cluster of white ones, and then there will be a hyperplane that passes through the closest point, black point. Yes, okay, so that's this blue, yeah. That's this one, right? The closest hyperplane that passes through the black point. Sorry. It should be like parallel to the red. Yeah, so it really should be like this, right? Yeah. And then the green one should be like this. Yeah. So why did I draw? Maybe maybe I didn't finish drawing this picture, and I got fine. So if you ignore what I've just confused myself, the blue one should be here, and the green one should be like this, and I want to squeeze out the red. Oh, I'm surprised I had this. Okay, some AI went wrong somewhere. Something goes wrong, blame AI. And of course, this is you should. Yeah, I think maybe that's.
two things that are completely random.
until you find. Yeah, I think so.
Initially, you don't.
That should have the picture, yeah. We'll trust her. Sounds good to me. That's right. But the point is this translates to an optimization problem of finding the distance of these planes and to squeeze out the red one. So this is called a support vector machine. This is, I mean, the reason I haven't thought about this is because this is implemented so well. It's one line PyTorch at dot svm bracket done, and then it will find this problem for you. But the idea is that given this data in high dimension, so I've drawn this in a very deceptive too. The point is that if your data points are labeled in two categories, for example, in very high dimension, you have no idea, right, where to find this hyperplane. You can't even visualize it. This algorithm will find that separating hyperplane by finding this point.
Data actually separates?
No, it will find the best one. It'll find the best value of this. So even if they're intertwined, it'll still try to find some. It's like when you have this completely random thing, you can still find the best fit straight line. It just doesn't look in any way like the best fit line. But I guess you could find all of the distances of these two categories to this point. Once you find this hyperplane, you can easily find all of the distances. And then you can see whether the distances are in any sense good. But it doesn't guarantee that they do separate. So but I guess you can do something like, you can find clusters. There are clusters, they're like, various things like, by finding center of mass for these things, and you can see whether the clustering is another algorithm you can probably do first to see whether there are indeed different clusters by just simply finding the center of gravity are different, center of mass are different, and then you do the support vector machine to find this actual separating hyperplane. Yeah, so this is very good because you actually get something out of it. One reason I would like this very much is because at the end of the day, this algorithm returns the functional form of this red hyperplane. You can just write it down. And that's very important for certain types of data. So I want to emphasize this because this was the algorithm we used. This is the joint work with Min-Young Kim, like in 2019, when we just literally plotted the space of finite groups in a certain representation, and we labeled simple ones. And we found a separating hyperplane between the simple ones and non-simple ones. Not a hyperplane, a curved hypersurface. And that was unexpected. I have no idea what that even means. But that's a proto-conjecture about the distribution of finite groups, which is unexpected. So that's what I'm saying. Now you can, what they put, once, of course, you can sometimes you don't have a hyperplane, you can have maybe a curved thing. And then in this language is called you add a kernel, right? Add an extra bit. The other one that I really wanted to emphasize was this. I think this is Kyuhwan's favorite thing, the PCA. I think Kyuhwan gave a very nice introduction. You were most of you here for his introduction. Kyuhwan gave. So this is just again to emphasize again what a PCA is. Again, this is so here is actually this is not necessarily labeled. So this is not necessarily supervised learning. This is just you're given a large set of point cloud, a large point cloud in huge dimension, and you can't visualize it. Just simply, if n is 100, how do you visualize that? So PCA was a method of reducing this data by projecting onto say 2 dimensions where you can actually observe something, right? So typically what you do is, well, you start with a set of vectors in Rn, and you want to output a set of vectors in Rl, where L is much smaller than n. So the PCA does this by a simple linear transformation, right? So you take your data, you transform your original data by some non-square matrix by mapping it to a smaller dimension. And what you do here, you simply, well, this is sort of an orthogonal matrix, but it's not square, so it's not a SO matrix. But then you minimize this variance. So in some sense, it's, how should I say, it's like a big blob of data. You transform each individual vector, project it to a much smaller dimension, and try to minimize the this variance matrix. Once you do that, you, in the best world scenario, you will see that the projection will have a pattern that's that you wouldn't have seen in high dimension. So for example, if your high dimensional data clustered, for example, and you can't visualize it, you just see a bunch of like 100 vectors, how are you gonna, it clustered in a particular way. You do this transformation, and then you can actually visualize that its projection onto the plane goes into certain regions. So that's the PCA. So each region is called a principal component because you've done this in a visualizable way. So these are the two things I'm going to really so the three things I'm going to use over and over again are simple feed-forward neural networks, or MLPs, multi-layer perceptrons, of not too many layers, and of very simple hyperbolic tangent or ReLU activation. These are type things we're going to use. SVMs, in the case of finding separating hyperplanes between labeled data, and three, principal analysis, where we project blobs of data to say 2 dimensions, which we visualize. I think these things are already very powerful things for us to try to deal with high dimensional data. So I think I'll stop here for now.
I just want to come back to the prime planning function again. Sorry. So when you said you try to like get the match to prime planning function, is it that you weren't trying to prove Riemann hypothesis, were you? Or
no, never dared to do that.
okay.
I mean, so this is yeah. There was a paper a few years ago. I can't remember the author, entitled "A Neural Network Search for the Riemann Zeros," but I think it wasn't very conclusive because we know the first 10 to the 10 critical zeros. I mean, what can you say? I mean, you can feed that into a network. It didn't find anything totally unexpected. This kind of experiment, it's obviously not going to raise any proofs for you, but what we're hoping for is that this kind of these kind of techniques on mathematical data will help us raise conjectures, which we then can prove. This is very much in line with the DeepMind collaboration in 2022, not last year, on knots and finding things. So I will mention something called memorations, which really was guided by this kind of experimentation. This memoration with Kyuhwan and Tom, and
so the question I kind of had was that the estimation curve that you actually get from the Riemann, if the Riemann hypothesis is true, I think the largest error term, or the error term is bounded by log of x,
something like that,
right? So what is the closest error term that you could get to when you try to take the prime planning function? Because if you reach log of x, then Riemann, but I just wonder how close you actually got to it.
That's a good question. In fact, we should rephrase your question in a way. We should try to rephrase your question in a way for a neural network.
Okay.
What property must a neural network have in order to have that log n correction? This I don't know. I think it would be nice to explore that. I don't know.
And also kind of related to what Albrecht mentioned, like if you work, say, for example, on function fields, finite fields, where the Riemann hypothesis is true, is there a way you can actually see this in terms of trying to I don't know anything about artificial intelligence, but can you artificially see that the Riemann hypothesis is true on function fields?
I'm sure you can visualize it in some way. I'm sure you can find a clever way of seeing that. Yeah. But whether that even involves a neural network, I don't know. Maybe we could just plot. Yeah, I think you should be able to do that. I mean, our explorations with L functions already kind of, so this is conditional on BSD, this is conditional on RH. You see this growth rate. This kind of things I think you can see. I think our question is, how do you rephrase that into that? I think that would be great fun to try.
I know nothing.
I don't know, but we can explore. That would be really cool to try.
Birch threshold or whatever, Birch test.
What's the Birch test?
And the Birch test is basically whether this investigation using artificial intelligence have given something which is maybe, I think Birch would say it's something that we should prove and have to prove, and it's provable. And he said so far that hasn't happened. Is that, I mean, what is your take on this?
So far it hasn't happened that we find.
Yeah, that you sort of that you found something that would pass this Birch test. But maybe you have a different opinion.
So I still don't. So the test is
to give a mathematician an observation he's far from, is new,
yeah,
provable and interesting. I think that was the test.
From finding from
large data analysis, whatever.
Oh no, I think memorization will be.
Well, he excluded that.
Unfortunately, excluded memorization.
Well, he said it's just barely makes it. I mean, he was not.
His point was that
Oh, I missed it. He's here. He was here.
It was no. I mean, I think he it was close. Yeah, that is close. But he sort of.
I mean, he denied it because he didn't use the AI.
Yeah, that's.
I see. Oh, no, sure. I see what you mean. Yeah. It was AI inspired and then human interpreted.
Right,
That was yeah. So it wasn't completely AI, of course.
Sept mentioned the three.
Yeah.
One was not theory.
Yeah.
And that's already something. And then actually the paper has something new in representative theory. The paper by Davis and other people had two examples, one in knot theory and the other in representation theory. But the impacting representation theory may be, I don't know how useful impact is. But anyway, this method finds out something new. Knot theory, I'm not theorist, but there is something. And I believe it's the beginning. In AI, the use of AI is in the kindergarten stage. So if it becomes like a teenager, then what happens, we don't know yet. So
That's right.
the memorization is kind of
An example.
Yeah, another example, but
This sort of hand of sort of.
yeah.
You used normal.
The one with Mignon, the one with plotting finite groups, that there's a separation between simple and finite. That's but the problem with that one, it's not, we can't quite put that into concrete conjecture, because I mean, we can tell you an algorithm of what we did, but can we phrase that in a way that a representation theorist can sit down to prove? Not yet, but we would love to have stated that. So I think that's also on the verge of the Birch test.
Right. I mean, I think.
Why is it called the Birch test? Just
because
Birch...
I think he was asking Birch what would be, let's say, something that would make an impact.
Yes, they are.
I mean, it was very critical, but I'm sure you're right. This thing is evolving so quickly that we cannot say.
I guess combining, like homology surfaces, I guess then you can use some AI to find out the region that you can do, and then conjecture an explicit formula. But I'm not sure how useful that is.
The bar
Quite possible. Yeah, of course. But I think that's exactly where we are now. I mean, this is really, this entire field is only a couple of years old. Of just at what point we can raise a major conjecture that would get all mathematicians interested in, because I think it's almost impossible to come up with something like Riemann hypothesis or BSD anymore just by looking into your eyes, because somebody was done of that level. Really?
I mean, of course, the people.
Yeah, exactly. We just have to keep trying. We have a lot of data. We have to keep trying. I mean, if you just plotted primes in some elementary way, and I tried it a lot of this, or even do binary representations of numbers and select the prime or whatnot. It's very difficult to find new patterns in that.
I was surprised by this talk of Brandon Hassett. He said that these people, Gauss and these people, they actually made this. This is amazing.
10 million by hand, right? It took me
10 million, but I mean, 10 million was 250 years ago. It wasn't reached. But then Gauss was making big tables.
How did he even do this?
Oh, just without he was insisting not to do without But he really looked at.
Yeah, absolutely.
I found this aspect interesting that he said it started actually long ago.
Yeah, exactly.
I heard of that story of those twin brothers with the communicating banks.
Sorry.
There was this twin brother.
Just like so there were these twin brothers in 60s and they used to communicate to each other in primes.
Oh yeah. There's a study actually in psychology, I think, I come with one of the journals on idiot savants. Why can they factorize numbers so quickly?
Yeah,
I don't know what the conclusion
to the
is.
order of like 10 to the power,
Yeah.
20 digits or something.
Yeah. How are they doing it?
Yeah,
They don't know. No, they can't explain why.
they can't explain.
So maybe there is a pattern.
I mean, yeah, exactly, because it's somehow it's in the brain,
Mhm.
which is even better than like Riemann.
Anyhow, sure. Thank you.